Hey, good people. Arthur Morris here. Hope all is well. In this video, we are going to look at evaluating limits analytically. So Theorem 1.1 here, some basic limits. Let b and c be real numbers and n be a positive integer. The limit of b, some real number b, as x approaches some number c, is just going to be b. Okay, number two here, let the limit of some variable x as x approaches some real number c is equal to that number c. And three, the limit of x to the nth power as x approaches some real number c is c to the nth power. Theorem 1.2, properties of limits. Let b and c be real numbers and let n be a positive integer and let f and g be functions with the limits. All right, so the limit of the function x in this case, as x approaches c, we're going to call that capital L. So, and the value of the limit of g of x as x approaches some number c, we're calling that capital K. All right, so the scalar multiple rule, if we have the limit of some number being multiplied times f of x as x approaches c, then we find the limit of the function and we multiply by that number b, whatever b was. Number two says if we're adding, they have a limit of f of x plus g of x, or the sum of the difference of two functions as x approaches some number c, then we find the limit of each one of those functions as x approaches c, and then we add or subtract those results. Number three, the product rule says the limit of f of x times g of x as x approaches c. Then we find, again, we find the limit of each one of those functions as x approaches c, and then we multiply those together. So capital L times capital K. And for the quotient rule, the limit of f of x over g of x as x approaches some number c. As we said before, we want to find the limit of each one of those functions as x approaches c, and then divide those results. Capital L divided by capital K, where K cannot be equal to 0, because remember, dividing by 0 is undefined. And number 5, the power rule, the limit of f of x raised to the nth power as x approaches c. Again, we find the value of the limit, and then we raise it to that power. Okay. All right, so let's look at some example problems. All right, so this first problem here, to find the limit of x to the third as x approaches 2. Now, the first way we always try to find the limit is to use simple substitution. So whatever x is approaching, we take that number, plug it in for x, and hopefully, if it's not undefined, then that would be our limit. So let's see here. So 2 to the third power, because we were approaching 2, and we had the exponent of 3, is 8. That's the limit. All right, number 7 over here, we have the limit of 2x minus 1 as x approaches 0. Again, if we can substitute in whatever x is approaching and replace that variable and simplify, we're good. Okay, so 2 times 0 minus 1. 2 times 0 is 0, and 0 minus 1 is negative 1. And that little symbol is an arrow. My daughter tells me it looks like a smiley face, but it's an arrow. All right, the next one down here, we have the limit of 5 times tangent of x as x approaches 0. So we have a scalar multiple here. And we still want to substitute in if we can. So we want to find, let's rewrite this as 5 times the limit as x approaches 0 of tangent of x. All right, so to simplify that, we have 5 times tangent of 0 and tan of 0 is 0. So 5 times 0 equals 0. So the limit of 5 times tangent of x as x approaches 0 is 0. Alrighty, next one we have over here is the limit of cosine 3x as x approaches pi. Again, if we can substitute and simplify, then that's what we do. That's the easiest and quickest way to find the limit if it works out for us. So let's come down here and we have the cosine of 3 pi, and the cosine of 3 pi is equal to negative 1. So the limit of cosine 3x as x approaches pi is equal to negative 1. Alrighty, the next problem we have down here, and you may want to pause the video and write this out before we get started. Alright, so we are given, let's put a blue line in between there. We are given the limit of f of x as x approaches c. We're told that that value is 2. And the limit of g of x as x approaches c, we're told that value of that limit is 3/4. So we're given the values of the limit. So we don't have to calculate any limits in this particular problem. We just need to use those rules that we learned, the scalar and the product rule and all of those rules, and simplify these. All right, so the limit of 4 times f of x as x approaches c, well, the limit of f of x as x approaches c is 2 from what we were given. So that's simply 4 times 2 is equal to 8. All right, what about the limit of f of x plus g of x as x approaches c? Well, that's our sum rule, and all we have to do is to find the limit of each one of the functions, which we are given that. So the limit of f of x in this case is 2. The limit of g of x is 3/4. So 2 3/4 or 11/4. If we write that in fraction form. Alrighty, part C. The limit of f of x times g of x. So this product rule as x approaches c, product rule, find the limit of each function and multiply those values together. So the limit of f of x in this case is 2. The limit of g of x in this case is 3/4. So 2 times 3/4, you can simplify, that gives you 6/4 or 3/2. And part D, the limit of f of x over g of x as x approaches c. We're looking at the quotient rule here. So we're going to divide the resulting limits. So we would have 2 divided by 3/4. And to divide fractions, we multiply by the reciprocal of the fraction that's being divided. So 2 times 4/3 is 8/3. All right. All right, moving on. All right, moving on to the dividing out technique. So the dividing out technique, again, the first thing we try to do is substitute in, but if you look at number 47 here, I have the limit of x over x squared minus x as x approaches 0. If I replace the x with 0 in my denominator, I will end up with 0 in my denominator, which is undefined. So we can't find the limit of this problem by using just substitution, not initially anyway. But if we can factor and simplify and then substitute, that still works out for us. So I'm going to take this and factor my denominator. So x squared minus x, I'm going to factor out an x. Gives me x times x minus 1. And then I'm going to cancel the x's in my numerator and my denominator. So this x with that x. So now I have the limit of 1 over x minus 1 as x approaches 0. Now we want to substitute and see if we can substitute in, and that'll work. So if we replace x with 0 now, so now we have 1 over 0 minus 1, and we get negative 1. So the limit as x approaches 0 for that function is negative 1. Looks like we do have some type of asymptote there, which we'll look at later on. All right, number 49, same type of problem. You see, if we take the 4x is approaching 4 and we plug that 4 in, or substitute that 4 in for x in our denominator, 4 squared is 16, 16 minus 16 is 0. We cannot divide by 0. So the next thing that we try to do is to simplify this fraction. So I'm going to factor. So x squared minus 16 factors to difference of squares, x plus 4 times x minus 4. Okay, now I can simplify the x minus 4 in my numerator and my denominator. It gives me 1 over x plus 4. And now I'm going to try to substitute the 4 that x is approaching in for the x in my function. So we get 1/8. Okay, so that's the dividing out technique. The next technique that we're going to look at is the rationalizing technique. So when you see a radical in one of these problems and you try to substitute in first and that doesn't work, then the next thing you can do is to try to rationalize to get rid of that radical, to see if that helps you out and see if you can substitute after that. So we want to try to get rid of that radical in our denominator, so we're going to multiply by the, in our numerator, sorry. So we're going to multiply by the conjugate of our numerator. Since this is a binomial, we'll multiply by the conjugate of our numerator. Okay, now we need to multiply the top all the way out using the conjugate rule that says if we're multiplying a plus b times a minus b, then that simplifies to be a squared minus b squared. Instead of using the FOIL and all of that stuff, we're going to use that shortcut that we know. So the square root of x plus 5 times the square root of x plus 5 is simply x plus 5. Anytime you multiply a radical times itself, you just get what's underneath. So remember that rule as well. The square root of x times the square root of x is simply x. So the square root of x plus 5 times the square root of x plus 5, or the square root of x plus 5 squared, is x plus 5. So let's just write that out. So x plus 5 squared minus 3 squared. And then in my denominator, I'm not going to multiply that out, because my goal, hopefully, is to get rid of that x minus 4, since that was causing the problem for me not to be able to substitute. All right, so the square root of x plus 5 squared is simply x plus 5. And then 3 squared is 9. All right, simplify the numerator. At 5 minus 9 here is negative 4. So x minus 4. Yay, that looks good. And I I didn't need parentheses in the numerator since nothing else was up there. So awesome. So we have x minus 4 in our numerator, and then we have x minus 4 in our denominator. That's a factor down there. So that means we can cancel out those x minus 4's. And that leaves us with 1 over the square root of x plus 5 plus 3. Now, what that allows us to do is to substitute in for x, replace the x with 4, and simplify to find the limit. All right, so 1 over the square root of 9. 4 plus 5 is 9. The square root of 9 is 3. So we have 1 over 3 plus 3, which gives us 1 over 6. So it worked out. So we had to rationalize first by multiplying the conjugate by the conjugate. And we use a plus b times a minus b rule, which is a squared plus b squared, to multiply the numerator out, those conjugates. And then we simplified, which allowed us to cancel the x minus 4's, which allowed us to substitute to find the limit. All right, all right, all right. Let's see what we have next. The squeeze theorem. And this one we're just going to kind of look at. The squeeze theorem says if f of x is greater than or equal to h of x and less than or equal to g of x, then if h of x and g of x have the same limit as x approaches c, then f of x also equals that same limit as x approaches c. So it just squeezes in. So f of x is here in between. G of x is greater. This g of x function is bigger, is on top, and the h of x function is on the bottom. So at c, as x approaches c right here, if g of x and h of x have the same limit as x approaches c right there, then it only makes sense, since they're squeezing f is in the middle, that f of x will also have the same limit as x approaches c. And that is the squeeze theorem, and that's theorem 1.8 right there. It says that if the h of x and g of x have the same limit L as x approaches c, then the limit of f of x exists and is also equal to L. All right, just be aware of the squeeze theorem. And then special trigonometric limits, we have two. I just want you to be aware of. It says that they say that the limit of sine of x over x as x approaches 0 equals 1. And the limit of 1 minus cosine of x over x as x approaches 0 is 0. Okay, so you may want to, let's see here, may want to write those down. Pause the video there and write those down. Alrighty, let's look at a couple more problems, and then that's going to wrap this video up. So number 63 here, we have the limit of 5 over x, the limit of sine of x over 5x as x approaches 0. So I'm going to use my scalar multiple rule first, since I have this 5x here and I know that I have an understood 1 there. I'm going to rewrite this as 1 over 5 times sine of x, writing too fast, sine of x over x. Now, what that allows me to do is to pull that 1/5 out and find the limit of sine of x over x as x approaches 0, and then multiply that result by 1/5. So if we go back just to the page before, we have this theorem here that says the sine of x over x as x approaches 0 equals 1. Alrighty, so I know that this whole thing here equals 1. So 1/5 times 1 equals 1/5. All right, and the last problem is the limits of cosine theta times tangent theta all over theta as theta approaches zero. So we got to start manipulating and simplifying this thing. And the first thing we want to do is to rewrite that tangent of theta as sine over cosine. So we have cosine of theta, and then we have tangent of theta. And we can rewrite that as sine of theta over cosine of theta, all over theta. And now we can simplify because we can cancel out the cosines of theta. And that gives us the limit of theta as theta approaches zero. We can cancel out the cosine of theta there and there. Now we have the sine of theta all over theta. And that goes back to that theorem that said sine of x over x as x approaches zero, treat theta the same way. That is equal to 1. The limit of that is equal to 1. All righty, good people. That's a wrap for this video. I hope you found it to be helpful. Thank you and see you on the next one.